Hey, what's up guys? My name is Cherno and welcome to episode 100 of game programming. 100 episodes. Can you guys believe that? Crazy stuff. So today we are going to do the A-star search algorithm from start to finish completely in this episode, no matter how long it takes us, and it's going to take us a while. So what we've got right now is we've got this node class, right? So I want you guys to take a good look at that if you don't have that already. That was the previous episode. And then we also talked about vector2i in another episode. These are the two main classes that we're going to use in conjunction with the A-star search algorithm to actually get it to work properly and to work the way that we want it to work, okay? So what I'm going to do is I'm actually going to close every other class that we don't need. So we only need level, which is where we will, of course, implement the actual algorithm, vector2i, and node. Okay, so what we're going to do today is basically just implement it in the sense of we're not actually going to do stuff like I guess waypoints and stuff like that, but and we certainly won't get mobs to follow those waypoints just yet. We're actually just going to focus on the actual algorithm itself and getting it to find a path. Now, what we do with the path we'll probably cover in next episode. Okay, so in the level class, we've got a bunch of methods here that we've already made, such as get players, get entities, methods that really have something to do with level in the sense that it allows the level to give us some kind of data, since every entity, and that includes the player or any mob, any entity that's in the level, it's you know, it has to be in the level, right? If we actually if we actually just open our entity class here, you'll see that we have an init, right? Initialize method that takes level as a parameter. So every time that we actually add an entity to the level, we have to give the entity a copy of that level so that we can then use that level to manipulate the entity, okay? So similarly like this is why the A-star search algorithm is going into I guess the level class. It's because the level is what's going to, you know, find the path at, okay? Because the whole point of this A-star search algorithm is to provide, I guess, the entity or an entity, a means of getting to another point on the level, okay? So therefore, since the level has all that data that we need, such as any other entities, things like walls, things that we can't get through, that's why the A-star search algorithm is actually going to be inside this level class. Now, in order to achieve this, well, I guess I'm just going to start off here. I'm probably just going to go down here into maybe just above get entities here. I'm just going to make a public list of nodes, and I'll just call this find path, okay? And we're actually going to take in two parameters, okay? The vector 2i of where we should start, okay? And the vector 2i of where we should, well, finish, I guess, where we want to end up with our goal, okay? So what we're doing is with this method, we are going to return an array list of nodes, okay? Nodes being these things, okay? Not vectors, not an array list of vectors, but an array list of nodes. And nodes have a vector, remember, but they also have other important details here that we'll talk about, such as a parent primarily here. Okay, so let's start with this thing, right? So let's first of all import vector since we need that stuff. Okay, brilliant. So the way that the A-star search algorithm operates, I'm not going to spend too much on how it actually works because that could take hours. I might make an in-depth episode that really actually like covers it with diagrams and stuff like that if you guys really want me to do that. But essentially, the way that it works is, first of all, there are two array lists, okay? One's called the open list, and we'll just set that equal to new array list node. And then we've got another one which is called the closed list, okay? Or the closed list, okay? And I'll explain what these are in a second briefly. All right. So the idea is open list are all like the tiles or the areas. In fact, you know, let's do this really quickly. I'll just open the game real quick so I can illustrate this to you guys. So we've got this game, obviously, right? Every tile as we see it right now is a potential like place that the A-star search algorithm can consider when it's working out a path. So what we need to do here, and what this open and closed list stuff is open list is every kind of tile in this instance. Of course, the A-star search algorithm doesn't actually have to deal with tiles per se, but in this case it is. So every tile here that we consider is actually put into the open list, all right? And then what we do is we kind of remove them one by one from the open list, put them into the closed list. The closed list being, don't look at that tile anymore. It's been outlawed or something. But the open list is the tiles that we're currently considering. And the way that the A-star search algorithm will actually work is it will consider all the adjacencies of the tiles. So in other words, all the neighboring tiles of a particular tile. And it will put them into the open list, and then we'll actually go through each of them if we need to and find the one that is actually closest to our goal. So for example, if we're trying to get from this one over here to this one over here, then what we'll do is we'll add this one to the open list. We'll actually consider all the, and then we'll actually put it into the closed list. So once we're considering this tile, we'll pop it into the closed list, and then what we'll do is we'll pop each one of these 8 adjacencies into the, okay, we're ignoring walls here, but anyway, into the open list, and then we'll consider each of them, and then we'll find, okay, this one over here is really close to the goal, so we'll just start off with this one, okay? Then this one gets moved, these other ones will get moved to the closed list, and this one continues. It's pretty complicated, but hopefully you guys will get this in a minute. Okay, so anyway, we also need a way to keep track of the node that we're currently considering. So I just like to make a node called current. That's the node that we're currently looking at. So in other words, the node that that we're up to, I guess, in this path. We'll set it equal to new node, okay? And the reason we're setting this stuff up is because this is the very start of our A-star search algorithm. So in other words, when the algorithm first starts, this is actually where we're going to, this is like the initialization of it, okay? So we need a place to start, and that is this parameter. So we'll make a new node with the vector here being start. If we go back to our node, you can see that our first parameter here is a vector. We also need a parent. Now, because this is the beginning, the start, there is no parent. So we'll simply set that equal to null. Very, very simple stuff. Nothing fancy here. What else do we need? So the G cost, okay, will be 0. Well, actually, pretty much everything's going to be 0, except actually for the H cost. So remember, the G cost is the cost since the start, essentially. And we're at the start, so clearly that's going to be 0. Now, this is where it comes into the H cost, okay? And the H cost being the cost from the start, an estimate from the cost, an estimate of the cost from the start to the finish, okay? Now, to do that, we actually need to simply find out the distance between the start and the goal, okay? I don't think we've got any methods here yet. No, we don't. So we'll make a, we should probably make this private, shouldn't we? Yeah. You know what we'll do? We'll make a private method here called, it'll return a double actually. We'll call it getDistance. And it's actually just in charge of getting, I guess, the distance between two vectors. So vector 2i, oh, you know what we could do actually? Yeah. I think what we could do, I'm just thinking, would it be better to put it into the vector class? So we've already got stuff like subtract. We've got, you know what, we won't confuse ourselves. We'll just leave it here. So I guess the distance between a tile and the goal. Okay, so any kind of tile and the goal. It doesn't have to be a tile. Just vector 1, vector 2. I just didn't want to call them vector 1, vector 2. So we'll make it. This is just going to be some simple Pythagoras theorem here. So math dot. Oh, we don't need that actually. So just it's simply tile dot x minus goal dot x, right? And then dy will be tile dot y minus goal dot y. And then of course we'll just simply return the square root of that. Oh, the square root of both of them squared. So dx times dx, which is why we don't need the math.abs here. Oh, we need to change this to getx, don't we? Is that? Yeah, okay. My bad. And get y. And get y. Okay. So that's why we don't need the absolute value here, because even if this value is negative, it's actually just going to get squared here, which will make it positive anyway, since anything squared is positive. Plus dy times dy. Okay? And that's it. So that will actually just figure out the distance. Now, why we call it an estimate, I guess, or like a heuristic value here, is because the reason it's heuristic and the reason it's an estimate is because we're figuring out the exact distance. So if we're trying to get from where the player is right now to this little thing over here, there's obviously a wall in the way. Now we can't simply be like, oh, that's fine. You know what? The distance to the finish will simply be, we'll go up here, then here, then here, and then that's the distance of the finish. We'll just work it out that way. Well, we can't, okay? Because the whole aspect of the whole reason we're using this A-style search algorithm is to find the path to the finish, because we don't know it right now. So that's why we can't simply be like, yeah, we can find out the direct way to get to the finish. We can't. That's actually what we're in the process of figuring out. So what we'll do is we'll actually we'll guess. So we'll say, okay, well, here's the player right now. There's the finish. We're just going to draw a straight line and we're going to figure out that distance. That's going to be our H cost, our guess. All right, so now that we've done that, we can simply type in get distance, the two vectors being start and goal. Okay, that's it. Simple as that. Done. Okay, great. So now what we have to do is add this current node into the open list. So open list dot add current. And that's pretty much all of the initialization code for this A-style search algorithm. Okay, that's it. The next step is going to be actually, I guess, working out all this stuff. Now, because it needs to kind of loop over itself and check every single tile it needs to check, we use a while loop for that, okay? And we actually keep checking for a way to get to the finish as long as this open list isn't empty. So in other words, if open list while open list dot size, right, is greater than 0, so once, well, there's something to look at here, we'll actually just continue searching for a path. Now, if all of the tiles that we add into the open list, or all of the nodes that it doesn't matter, node equals tile in our case, any of the tiles or nodes that we add into our open list, if that open list becomes empty, that means that there is actually no path to the finish. Of course, that happens sometimes, right? If you've locked yourself in a room, you can't expect to get out. So that's why we have obviously there is a scenario in which this while thing will finish. Now, that's not the only exit strategy here. We want to stop looking for a path when there's no path, which is what we've written here, or if we find the path, right? As soon as we find a way out, as soon as we've found the path, we want to just return it straight away, okay? And what I'll do here is I'll just say quickly, just so we can get out of this, if current dot, so current is our current node, so if our current node, and we can actually get our tile, which is our vector, dot equals, and we'll have to set up an equals method in a minute, but if it equals goal, okay, if it equals this one, so if the place that we're currently checking is the actual finish, then we essentially need to return here, okay? And we'll talk a little about this in the, well, not in the next episode, but later on in this episode, but not just quite now, because this is the finish. We're not up to that yet. Okay, so what we need to do is set the current tile, because it's currently this. That's cool. We actually need to set it every loop. We need to set it to the very first node in the open list. So in other words, we'll just set it equal to, current equals open list dot get 0, okay? So that will return the very first node in this array list. Now, in this case, of course, current, we've added current into open list, and then we're setting current equal to open list dot get 0. It will simply, current will actually equal this current on the first run, but obviously on each sequential run, it won't, okay? So so why are we getting the very first node? Why are we doing this? Why can't we just, I don't know, why don't we, because obviously, let's just say that we're in the middle of a field, we'll get 8 adjacent tiles, so why aren't we getting one of those tiles, right? Why specifically number 0? Why specifically the very first one? Well, the reason is, what we do just prior to this is actually sorting these tiles. We'll actually sort out all of these nodes that are in the open list that are freshly added, that you'll see in a minute. We're actually going to sort them out in order of closest to furthest from the finish, okay? So in other words, what we want to do is, since A star is all about figuring out the closest or the shortest, the lowest cost path to the finish, we want to consider the tiles that are closest to the finish first. And that's where performance comes into play. We could eventually check every single tile on the bloody map, and then of course we'd find a good way, but we just want to, we kind of want to give the tiles that are actually closer to the finish the priority here. So what we need to do is write a quick comparator that actually will sort out, right? We need to write some kind of sorter that will actually order all of these tiles from I guess the furthest from the finish to the shortest to the finish to the furthest from the finish, so that we consider the ones that are closer first. The way that I'm going to do that is I'm just going to write a private comparator up here. So I'll go to where all of our fields are, and what I'll do here is I'll simply write a comparator here. So in other words, it'll be kind of static here, kind of. So private comparator, and the comparator is all about comparing things, right? All it does, and we'll actually just make sure that it deals with nodes here. We'll call this, I guess we'll just call this node sorter, okay? It'll sort out our nodes. And we'll set this equal to new comparator node, okay? And what we'll do is we'll actually just straight away give it a body here, so that we can deal with this. Okay, let's import this, of course. There it is, sweet. All right, and then if we actually just hover our mouse over here, we can add the unimplemented methods, which is compare, okay? So what compare does here, okay, and I'll explain this in a minute because this will look really weird if you're kind of either new to Java or you've never used comparators before, because they're not, they're not very common. But essentially what a comparator does is it takes in two objects, okay? So in this case, it's going to take in two node objects. If we change this to integer, it's going to take in two integers. It's going to take in two node objects, and based on what we enter over here, it's either going to return, it's going to return an integer. Okay, so the way that we're going to utilize it is we'll just call this n0, so node, I guess 0 and node 1. Okay, these are the two nodes that we're comparing. So what we want to do is, because this will be used in conjunction with an array list, and then remember an array list is just a bunch of indexes. So what we want to do is since we want to sort it by so since we're sorting by shortest distance to the finish, by shortest cost to the finish, what we want to do is we want to sort it based on the F cost, right? Because the F cost is actually a combination of these two, and thus it is our actual cost, right? If we just sort it by G cost or just by H cost, we're not going to get the lowest cost. We're going to get the lowest either distance from the start or distance to the finish. We don't want to do that, okay? We want to get the shortest, combination of those two, because that's our total cost. So since we're sorting by total cost, what we essentially want to do is we want to check the node's F cost and say if it's lower than the other nodes. So in other words, if N0's F cost is lower than N1's F cost, we want to, we'd probably leave them the same. But essentially what we're saying is if let's just say if N1's F cost is lower than N0's F cost, switch them around, right? And the way we can do that is simply say if n1.fcost, which is what I just said, is actually less than n0's fcost. So in other words, the cost is less, thus the path is shorter. Then we can return 1, okay, or positive 1. I'll just put a plus here. It doesn't really matter, so you guys can see. However, if it's the other way around, so if n1's fcost is actually greater, we'll return a negative 1, okay. And what that will do otherwise, if they're the same, we'll just return 0. So what this is saying is, if n1's f cost is less than 0, then essentially we want to move it up in the index of the array. Otherwise, we want to move it down, okay? That's how this works, okay? It's pretty simple. So hopefully you guys understood that. I know I talked a lot. So now that we've made this comparator, it's not in use, obviously. We've just made a way to, compare two things. So in other words, we either based on what we're comparing here, we're either returning positive 1 or negative 1, which is, the direction in the array which we want to move this node to. So now what we want to do, first up, is actually sort this. So, luckily in collections, which is the Java class, of course, we have an awesome method here. It's actually static, called sort, okay? And it takes in a list as an argument here. So in other words, we will sort our open list. And the other argument is a comparator, which is what we've just written. So node sorter. And that's it. So it's going to sort our open list based on what we've specified in the node sorter, which is, move the node further back if it has a higher F cost, and move it closer to the front if it has the lower F cost. And that will sort it in order from lowest F cost to highest F cost, which will ensure that the nodes that we check first, this is going to be such a long video, the nodes that we check first will actually be the ones that are closer or more efficient. All right, great. So let's move on. So we've done this to we've done these two. This is great, and this is our if we've reached the finished, return it. But if we haven't, we'll obviously continue here. So what we'll do is we'll actually remove. So open list dot remove the current. So in other words, what we're doing here, and we'll actually just add it to the close list. I'll explain this in a minute. So what we're doing here is we're actually just moving the current node from the open list to the close list. Okay, so we've checked it right now. Current is this. If current equals gold, great. If not, then let's remove it from the open list because we don't want to look at this tile again. We want to move it to the closed list. Okay, so these are the tiles that we've already checked. Okay, wonderful. And now this is where the real magic starts. We check every single adjacency, and adjacency is of course a directly connected tile. So there are 8. Okay, I'm sure I didn't need to bust out paint.net here and show you guys, but if we have, let's just quickly go ahead and change the canvas size here to, let's just go ahead and say 24 by 24. And then I'll quickly make a grid for you guys that is 8 pixels here. Right, so now that we've got these tiles here, right? So if our current node here, okay, our current node that is now in the closed list, but that's all right. It doesn't matter what list it's in right now. It's still our current variable here. If this is our current one that we're checking right here, this is the current one. The adjacent ones are of course going to be these. Okay, so it's going to check every one of these, and it's going to see if they're close to the finish or not. Now, very, very important, as it checks all of these adjacent nodes, adjacent tiles in this case, doesn't matter, again, node equals tile. I want you guys to, not in every circumstance, but in our one, node equals tile. As it's going to check all these, it needs to somehow not all of them are going to be valid. So if we happen to have a wall in the way, right, if this happens to be a wall here, then we obviously don't want to add that into the open list because we don't want to consider it. We can't go through a wall. What's the point of considering that? And also we definitely don't want to add, I guess we don't want to add it if it's already been in the closed list. So if we've just come from here, this is the previous check, right? This is where we were the previous iteration of this while loop. If we've just come from here and we've kind of just moved up in the world this way, this is where we come from. That is an arrow. That's an arrow. Yeah. If we've come from here, then we really probably don't want to check this one again. Why? We've just come from there. That's stupid. So don't check this one either. So the two things that we kind of need to ignore are tiles that are invalid and tiles that we've already visited. That's why we add these tiles into the closed list, so that we avoid looking at them again. So what we want to do here then is, first of all, we need to set up a for loop. So and the other one we don't want to check is the middle because we're there right now. So that's important. So for in I equals 0, actually, yeah, we'll just do I is less than 9, I plus plus. So what this will do, we could also do a nested for loop, but I'm pretty sure this is simple enough. So in other words, for each of these adjacencies, because remember there's 9 total tiles here, okay? A few of them we don't want to actually visit. So in other words, actually the one in the middle here, right? We want to skip that straight away. So if we look at how the for loop's going to pick this up, it's going to go ahead and go, this is going to be 0, that's going to be 1, that's going to be 2, that's going to be 3, that's going to be 4. Okay, so 4, index 4 is the middle. So if I is equal to 4, we'll continue. Okay, so we don't even want to hear about that because we're on there right now. We don't want to add that. We don't want to consider that one because we're there right now. If it was the finish, then we'd already be there. Okay, so now that we've done this, let's get the current location where we're at. So int x is going to be the current.tile.x. Get x. Actually, yes. Wait. Oh, we meant get it. Oh, so okay. We did private them. Okay, no problem. So we'll get the x. This is the vector, and we'll also get the y. So this is the current location of where we are right now. We'll get the y. We'll also get the, I guess, what do I call this? The direction, kind of. Okay, so, well, it is the direction, but, there's no, okay, well, this is kind of like the x direction. I'll just call it xi. But I mod 3 minus 1, okay? So what this will do is this will be either -1, 0, or 1. Okay? And same with y. Okay? So in other words, we'll use divided by for y, of course. This is a standard kind of grid horizontal / vertical thing. We'll call this yi. So what this will be is over here. This is becoming quite. Let me just kind of clear this, I guess. Just get rid of this stuff, kind of. Okay, cool. Clear this board. Okay, so over here, if we are over here, then x will be -1 and y will be -1 in this quadrant here. If we're over here, x will be 0 since we're 0. Y will still be -1. Okay, so it's relative to the center. 0, 0. This is 0, 0, right in the center here. This is -1 for x, 0, and +1 for x, +1 for x, +1 for x, since x is horizontal. 0 for x, 0 for x, and let me just draw a better 0. There we go. Probably get rid of these as well. No? Okay. This is not about drawing zeros. And this is -1. Okay, and that's obviously, that's -1 for x, okay? But for y, since, it looks like a 4. But for y, since we're going up and down with y, it's vertical, this will be a -1 for y, this will be a 0 for y, and this will be a +1 for y. So in other words, what we're doing is we're picking out the direction. Since we're dealing with tile precision and not pixel precision, if we want to move one tile to the left, so in other words, since we're considering all of these neighbors, all of these adjacencies, if we want to consider the one tile that's to our left, we can simply grab the current x position of the current tile and subtract 1 from it, and then that will actually land us onto this tile that we can now look at. So this is a way to, I guess, select the current neighbor that we're checking out, the current adjacency that we're checking out. So now that we've got these values here, we simply want to grab the current tile that we're at. I'm just going to call this at, okay? This is the tile that we're looking at right now, that we're considering currently in this current iteration of this for loop. So get tile x plus xi, y plus yi, okay? And of course, x is our current tile, and then xi is either -1, 1, or +1, depending on the iteration of this for loop. Same with y. Y is either -1, 0, or +1, okay? So in other words, this will make sure that this at thing will actually be every single tile in this list, except for the middle, because we skipped that over here, right? It'll be every single one at one point. So we'll consider all of these surrounding tiles. So first of all, if at equals null, if we're somehow gotten out of the map, or we couldn't actually get the tile at the particular location, you'll actually notice that we're using the get tile method, which simply returns a tile based on the, I guess the tile coordinate here. So, I guess that's useful, just to note that. We'll continue. Okay, so now that we're not null, we can actually do something. So we'll check it out and we'll say if at is solid, right? Then it's useless to us. It's a wall. We can't go there anyway, so what's the point of considering this? Continue. Okay, so the reason we haven't put this into one statement, by the way, is because if at is actually null and we consider this solid thing, that's a null pointer exception, so it'll crash. But this way we check that it's null first, and if it's not null, we can proceed. So if it's solid, we'll skip it. So now that it's not null and it's not solid, it's a valid tile for us, right? But is it the most efficient tile? Is it a tile that we haven't visited yet? Is it a viable tile, right? It's valid, but is it actually viable for us? So we'll create a new vector 2i. I'll just call this a, okay? This is literally the at tile, but as a vector. So new vector 2i, x plus xi, so exactly the same thing as this, right? It's this tile, but in vector form. Y plus yi. Okay, and then we'll figure out the g-cost for it. We'll actually have to figure out, well, both the g-cost and the h-cost. So our g-cost is very simple. Our g-cost is simply the current g-cost, which for the first iteration will be 0, plus the distance of the tile that we've just been at. So the current tile and the tile that we're considering. So this is the tile that we've, I guess, been at. This is the tile where we are right now, and this is the neighboring tile. Now, the way that this equation is set up is because we're simply comparing a distance of one tile to another directly. We're never comparing. We are never with this setup comparing the distance of here to here or here to here. Never. We're only comparing immediate distances, like I'm just drawing here right now. This is the only kind of distances we're comparing. Now, the reason that we're comparing, because we're comparing this kind of distance, it's either going to be positive 1, right, which is a distance of, I guess, horizontal or vertical, or if it's diagonal, since of course diagonal distances are greater, it's going to be the square root of 2, otherwise known as around 1.41, okay? So that's the way that's going to work, okay? But remember, if we've been here, okay, let's grab another color, blue. If we've been here and we've moved over here and then we're moving over here, right? What it will do is, since we have this current J-cost, it'll get the current J-cost, which, well, at the moment, I guess, if we're up to this one right here, if we're considering moving to this one, it'll grab the current J-cost, which is 1, and it'll just add on this distance, which is root 2. So it'll be root 2 plus 1, or I guess around 2.41 J-cost, okay? That's how the J-cost works, and I covered this previous episode. Now, the H-cost is, of course, an estimation from, I guess, our current location to the finish. So the way that gets worked out is also really simple. It's simply, and we don't need any current stuff. Remember, it's not a sum. It's not like a cumulative distance. It's just the get distance from A to the finish, which is the goal. Really simple stuff. That's the H cost. Okay, that's pretty much it. We're actually almost done, which is awesome. Well, no, because we have to cover the returning of stuff, but we'll do that in a minute. This is quite a special episode. I hope you guys are enjoying this. I'm almost out of breath here. So if, actually, let's first make the node. So node, we'll call it node. This is the node that we've made out of this data now. Because remember, a node requires a J-cost and an H-cost as well as a vector. So we've done everything. It also needs a parent, which is, well, viable now. So new node, with, of course, this vector here. The parent, okay? So the parent is the current node that we're comparing. Very simple stuff. So it is a node. We need a node for the parent. And the node is where we're at right now. So in other words, what happens here is, since we've gone through this, everything checks out, this seems legit, we might consider now moving from, let's just say we were here to, well, I guess to here, since we've already done that. Yeah, what it's going to do is it's going to parent, it's going to grab this as the parent of this node, because that's where we were last. Very simple, okay? And we also need the G-cost and the H-cost, and that's it. We've made a node. We've successfully made a node out of this. Great. So what we'll do now is we will, we'll add it to the open list, but we should check a few things first. So if it's already in the closed list, right, then we don't want to add it into the open list. Okay, so if we've already been there, now we have to check, have we already been in this thing? So the way that I like to do this is, because we're not checking, okay, so we could have done something like, if closed list dot contains, and then, you know, we obviously need to go with a node, so like node. But that's not what we're comparing. We're simply comparing if the vector is in the list, okay? So in other words, if this A vector is in the list, not the entire node. So we can't use this, okay? So what we have to do is write our own method here. So what I'll do is I'll make a private boolean called vec_in_list. This will check if a vector is in a list of nodes. So it'll take two parameters. Well, I guess list one. Oh no, yeah, just the list that we're looking for it in, and the actual vector that we're checking to see if it is in the list or not. Okay, and this is really simple. So for every node in the list, I could write a normal for loop, but I'm probably just going to go ahead and write a for each loop. So I usually don't do this because this sometimes causes problems, but it won't in this case. So in other words, for every single node, right? For every single node in this list, and we'll call it n. If n, so that's the node that we're currently looking at in this list, since we're looping through every node in there. If n.tile.equals vector, and we'll have to set up that equals method in a minute because it won't work. Then we'll return true. Otherwise, if we've gone through the entire list and it's not in there, we'll return false. This needs to be done. Remind me. Not that you guys can. This isn't live, but anyway. So if vec in list. So if inside the closed list we have this a vector, then well, we'll continue. But also, oh, but no, hang on. it's okay. The A star search algorithm also has one little bit that I'm not going to go into because it will take too long. It has one little other kind of quirk where a vector that was a tile that was previously marked closed can actually be reopened if in some circumstances, if there's really no other way, and this suddenly becomes viable. Like what seemed unviable is now viable again. Then we can actually reopen it. So in other words, we'll only skip it if, let me just write this out first, node.gcost. Okay, so continue. Okay, so continue of course means that we'll skip this current iteration of the for loop. So in other words, if the vector is already in the closed list, but the gcost, this gcost here, is greater, right, than this node's gcost, okay, which will tell us if it's greater than the gcost here, then this probably should be current gcost. If this gcost is greater than the current gcost, then we'll continue. I'll actually have to check. I'll have to double check this maths actually because this might be a bit wrong. But then we'll continue. Okay. But so in other words, it can get reopened if this is false. And I'll have to really double check this because I don't have this written down anyways. I'm just going off the top of my head, so I might have to actually test it, which I'll do in the next episode. But if a vector, okay, this is the other thing. If it's already in the open list, we don't want to add it again. We don't want to have a duplicate node in the open list. So if the open list does not contain, so in other words, if this vector is inside the open list, if that is false, so if the vector is not in the open list, or the gcost is less than current gcost, then we'll add it. Okay. No, it's not going to be current. I think it is node. I think it is node, because that's not going to make any sense if it was current. Again, though, I'll have to double check here because I don't think that will add up. Anyway, remind me to double check this. Let's do the return. So, what this will do, I kind of skip through this. If the vector is not in the closed list, if the vector is in the closed list, then we don't need to add it again, so we'll continue. However, if the vector, that's fine, but if the vector, unrelated here, if the vector is not in the open list, so if we've never actually, if it's not in there right now, if it is in the closed list, we're not going to add it. If it's not in the open list, then we will add it. Okay, so we don't want to add it. We obviously don't want to have duplicate nodes, but on the other hand, if it's not in the list, we will add it because we're going to consider it next. Okay, so what this will do is essentially give us, but it won't only add one node. We'll actually get about 4. But remember, once it does this, it's going to finish. Once it finishes all the adjacencies, it's going to finish this entire for loop, and then it's going to finish the while loop. So it's going to go back to the start, and then it's going to sort them, and then it's only going to consider the one with the lowest cost. So although we might add like 4 or even technically up to 8 nodes into the open list, we're only going to look at the one with the lowest cost. Okay, so let's talk about returning this. So what we have to do now is reconstruct the path. Okay, we found the finish, we need to reconstruct the path because we need to somehow, that's the whole point. We need to return an array list of nodes which will guide us to the finish. So we'll create an array list of nodes. I'll call this one path. This is what we're actually returning. This is the result. New array list path. So while, the parent of the current, okay, so the current is still being considered here because remember the current right now is the finish since we're in here. So if current dot parent, so if the parent of the current one is not null, now this is important. The only circumstance in which the parent is null is on the starting tile. It's where we've started. So this, basically what this will do is we're retracing our steps from the finish to the start. So in other words, keep on looping through this until we reach the start because we know that when we do reach the start, parent will be null. So we'll add the current tile to the path array. And then, of course, we need to backtrace it. So we need to go to the previous tile. And the way we do that is we simply set current equal to current.parent. Because parent stores the previous tile that we've been at. Right. I've clearly screwed something up here. Whoops, my bad. Okay, so that's what it's going to do. So it's going to actually loop back through all these, and as it goes back to the start, it's going to add all of the nodes that it visits to this path. And now we simply have to return the path. I also want to clear both of these lists from memory first, because sometimes garbage collector isn't great at that. And then we'll simply return this path that we've reconstructed, and that's it. Okay, that is the A-star search algorithm completed. I will have to double check these again, but roughly completed. Okay, so the other thing is, what was the other thing we wanted? Yes, the equals. So n.tile.equals. Equals, of course, right now, if we hover our mouse here, is an object. It's an object, I guess, method, right? We want to override that though, because we want to write our own equals method, because the object one will check every single piece of the object, and that's not what we want to do. We only want to check if essentially, because a vector, as far as we're concerned, a vector is only consistent of an x and y value. So we just need to check if those values are equal. Okay. So the way we can do that is we'll just go back here into vector 2i, and we'll down here at the very bottom, we will just make a public boolean equals, and we'll have to fit an object. So we're overriding the object one. So you'll see over here, hopefully. Let me just return false. That'll be the default, of course. So we'll just write that in. You should see Eclipse tells you that this is actually overriding the object thing. And if we click on that, okay, I don't have this source attached, but the object class in Java, which every single class inherits, the object class in Java has a method called equals, and we're just overriding it here. Okay, great. So first of all, this is really simple. So first of all, if the object here that we're looking at is not even an instance of a vector, instance of vector 2i. So if this object that we're considering is not even an instance of this class, then well, it's clearly not going to be equal. So let's just return false straight away. We don't even need it. Okay, now we need to cast it. So vector 2i, what's called vec, equals vector 2i object. So now what we're doing is we're saying that, okay, here we're checking to see if this object is actually a vector. If it's not, return false. If clearly this doesn't return, that means that it is a vector. So since it's a vector, let's just make sure that we treat it as a vector here. And then we'll simply go ahead and check if vector.x, we'll actually use getX. So if vector.getX is equal to this.getX, okay, and we could have just not used this, but anyway, and vec.gety is equal to this.gety, then we'll return true. So what we've done here, of course, is we've simply compared these two components of the vector, and if they're identical, if they're identical, then they are the same, so we'll return true. Otherwise, if they're not, we'll just return false. Okay, and that's it. So we've written our own equals method to override the Java one, because this is obviously going to be correct and the Java one won't be. Not for this case anyway. Okay, great. So one last thing we need to do, since this gives us an error, is return the default result. So in other words, if no path was found in this entire while loop, we will simply have to return null. Okay, and that's it. All right, and we'll actually, okay, open list will already be clear. We'll close list.clear. Open list will already be clear because the only reason we get out of this while loop is if the size of open list is less than or is 0. Okay, and if it's 0, it's empty already, so no point cleaning it. No point clearing it. Okay, that's it, guys. That is the A-star search algorithm in all its glory. I hope I explained it well. I may do an in-depth episode. It's pretty complicated, kind of. It's I don't know. It's dependent on what mood you're in, how complicated it is, honestly. But if you guys have if you guys know what's up with this, because I'll have to double check a few implementations. I'll probably test this out to see how it works. But drop a comment below, of course, if you know what's up with that. But anyway, guys, I hope you enjoyed 100 episodes of this series. This is by far probably the longest thing I've ever done in my life in terms of commitment wise. Can't even talk after this thing. Because I mean, what is it like? It's been a year. It's been over a year. It's been like a year and I think 2 months that I've been doing this for. This game programming series. So it's been a while, yeah, and I hope you guys enjoyed all 100 episodes, and here's to 100 more, because that's probably how long it's going to take, if not more. But I think it'll get a lot more fun very, very fast after we finish all this kind of boilerplate game logic code, and we can move into gameplay design, and things like multiplayer, and actually more testing, I guess, than coding. It'll get a lot more fun, and it'll just be an awesome change of pace, I think. Anyway, here's to a 45-minute episode. Probably never again. This is more of a 3D game programming thing to do, but I'll see you guys next time. Please hit the like button if you guys enjoyed this video, because obviously I put a lot of effort into this, and I'll see you guys next time. Goodbye.